Hi everyone, and welcome to this section 5 of CS188. So today we're going to talk about MDPs, and we are going to show how these become very interesting when we consider them in the context of reinforcement learning. So previously on MDPs, we assumed that we knew several things. So we assumed that we knew the transition function, and we also assumed that we knew the reward function. So basically here, we assume that we knew the dynamics of the world. And unfortunately, that's not a piece of information that can be available to us at all times. So what happens when these tables will have to infer from experience? Well, that's what we call reinforcement learning. So in RL, we're going to learn how to behave optimally in an unknown environment. And if we come back to our grid world, so for example, if you have these rewards, which we saw in the previous section, now, well, you assume that initially you don't know any of this. You're completely blind, you don't even know how to move, you don't know where to get a good reward, you don't know anything about this world. And yet, we are going to be able to learn two things. So first of all, how to move, what are the dynamics, and also what are the rewards, which will enable us to have an optimal behavior in terms of maximizing our expected utility. So there's a first thing that we can do. So we can try to go back to the framework of MDPs. And so what we can do is we can estimate the transition probability and the reward function. So the transition function is just a big table. So you can consider that if you see S and A, then you can update the likelihood that you will end up in S prime. This is going to be a sample, and basically what's going to happen is that T of S A S prime estimated is going to be the normalized number of occurrences of S prime if we choose A in state S. All right, and about the reward function, we can do the same thing. And here we don't need to normalize because we assume that this function is deterministic. So here it's a consequence of the modeling of the model we've chosen. Basically what's happening is that all the stochasticity is embedded in the transition function. And therefore here we just need to see it once to see. All right, so this is called model-driven model-driven RL. So basically here we estimate the probability function that models our dynamics. We also estimate the rewards, and then we solve the estimated MDP. So that's the first way to go, and in fact it turns out that we can do these two steps in just one. So now what we're going to do is we're going to try to consider directly our value function. So our value function, if we remember for example, the value estimation update for a given policy, we had this equation here, which meant that once our policy was devising an action to choose in state S, well, all that we were doing was averaging over this probability distribution here of transitions the utility we get after transition. So basically, this is an expectation under this probability function of this quantity here. And if we know the probability transition perfectly well, we can exactly compute this expectation. However, if we don't, well, we can still try to estimate this. And we hope that basically the law of large numbers is going to work for us. So that means that now, if we observe the reward, and this is going to be our sample, so basically, if at some point we end up in Si prime here, after having chosen the action prescribed by the policy in state S, so we assume we already have an estimate of the value function. What we can do is that we can compute an average over this empirically. And what we could do, as Inka mentioned, is just to say that now our next estimate for the value function will be an empirical averaging of these samples. However, the problem is that here we don't get to decide to be in S, okay? Because as we make decisions based on a policy, well, there are still stochastic events which are going to decide that we end up in a certain state instead of another one. So basically, we cannot teleport in a certain state. And what we do instead is that, well, we go with the flow, we follow a certain policy, and we are impacted by the randomness. Of the MDP, and we don't know the structure of its randomness. We don't even try to estimate this probability function. What we do, however, is that we're going to compute, instead of a classical average here, we're going to compute a moving average, and that's called temporal difference learning. As we get to a certain state S, well, we make a decision, see what happens next. So we get our sample here. And all that we're going to do is use this update for S. So we are going to re-inject the old value, but we are not going to give it a weight of 1, only 1 minus alpha. So typically this will be, something like 0.5. And you could also, and then what you do is that you give a weight of alpha to the new sample, which is this here. And basically, progressively, you're going to update this estimate of the value in state S for that policy. So that's called temporal difference learning, and that's how you can learn the value function associated to a given policy. And here you can see that we do not model P. We don't even estimate it. So the problem is that once you figured out a certain value function here, well, in fact, to be able to decide on which action is best, you would need to estimate the transition function, and that's not best, because that's what we're trying to avoid here. So what we're going to do is that instead of updating the estimates of the value, what we're going to do is that we're going to do Q-value iteration. And so remembering that the Q function is the expected utility after having decided to undertake action A instead S, we can write the theoretical value of this Q function. And then we can remember that if we decide to be optimal in our behavior, this value here is the max over the actions of the Q values in S prime. Okay, and that gives us this recursive definition of the Q value. So now if we start to think about the Q value the same way we did for the value function previously and try to estimate it empirically, what we can do is what's called Q-learning. Now we're going to compute this average, only our so what we're going to try to estimate is going to be Q. Now our sample, what is nice is that it's still what we had previously, only in terms of reward, only we re-inject the Q functions. And here what's going to happen is that because we assume that we have an optimal behavior, not only are we going to estimate the Q function, but also as a byproduct, we'll have an optimal policy. Here, what's really interesting is that we didn't have to infer the structure of our environment and the stochastic dynamics that we're dealing with, and how, in spite of that, we've been able to devise Q functions and therefore an optimal policy. And all we need to do, what's called Q-learning, is these updates that we could do for the value function, but it's in fact much better to do it in this case for the Q function. So when we see a new sample like this, we use it to update the Q value thanks to this running average. And as we have a choice for the alpha here, we give a name to this parameter and we call it the learning rate. So the reason why we chose this name is that it decides how much importance we give to new samples. And you can see here with this formula that basically what will happen is that if you have a high learning rate, well, you will incorporate new information faster, but you will have a value for the estimate of the Q function that will jitter more. And if you have a lower alpha, you will have a lower variance. But what's going to happen is that the value of Q may take more time to converge to the optimal value. So there's a trade-off here. Okay, so now let's tackle the problems and see how we can apply this in practice.